Now, much of what chemical and physical changes are, you already know. But yesterday we talked about physical change. You know what melting is, you know what freezing is. You know if wood burns, it becomes something else. You know, you're not sure specifically what it becomes, and it becomes a lot of different things. But you know, at least intuitively, because you've either learned it before or you've seen it in some way, depending on how many experiments you did, you know that if you burn wood perfectly in the presence of oxygen, you're going to produce carbon dioxide plus water plus energy plus a lot of other stuff. Plus stuff. Yes? One of the things you burn, and it's on the video that I made, is one of the you make is carbon monoxide. And why carbon monoxide is so important. Look up right now. Look up, Albie, look up the number, how many times more competitive is carbon monoxide than oxygen? And put it into Google just like that. Carbon monoxide, oxygen, which is more competitive by how much? Something like that. And you'll find that carbon monoxide is 80, I don't know, some enormous number more competitive. It's more competitive for the heme group. Iron. You have 6 coordination bonds, and oxygen goes on one of them. Yes? And it's a pressure sensitive bond. Yes? The higher the pressure, the more firmly it attaches. So then when it gets down into the capillaries where the pressure is reduced, it drops off. That's how it oxygenates your blood. Yes? So if you have really high blood pressure, it's not going to drop off. It may not. It may not oxygenate your vital organs well enough. And you could get damage to your vital organs. But carbon monoxide, for instance, one of the things that you make when you burn wood is a very, very, very dangerous gas. And they talk about it in the book. I'm not sure what chapter it is, but they talk about it in the book. But you know a lot of this stuff. Okay? You know that if I take wood and I burn it in the presence of oxygen, I'm going to produce carbon dioxide and water. You know that. And you know that you're going to get a lot of energy. You've seen fire. You've seen it. And you know that you're going to get a lot of energy released. Well, why do you get energy released? Does anybody know? It has, remember yesterday we talked about we're going to do stability. We're going to do energy, changes in energy. Remember, there were 2 driving forces in nature. What are they? Reduction of energy or increase in entropy. I know, go figure. S. Entropy is S. How does that figure? Right, exactly. E for energy, I understand that. But they don't even say energy. You know what they say? They say internal energy. Internal energy is H. This is enthalpy. This is entropy. Okay? This is enthalpy. This is entropy. Understood? That's going to be, we're either going to be only 2 driving forces in nature. Anything that happens, anything.
The one is going up, that's entropy.
You're going to increase, and driving force of nature is increased entropy or decreased enthalpy.
But, no.
This is what we're going to really talk about, really. We're not going to talk about this until we get more involved in chemistry. Maybe next year, the year after. Albie, what do you got?
It says carbon monoxide has 10 times greater affinity for
10 times?
210 times.
210 times. Is that what it says?
Sir, it says 210 times greater affinity for hemoglobin than oxygen.
Right. Hemoglobin was this. Hemoglobin is, this is an enzyme. They have 5 bonds. Actually, you have 4 parts of the of the globin. It's like a giant protein, right? It's the red blood cells, a giant protein. It's called a globular protein. And the iron is attached in 4 sites. Then you have these 2 open bonds. One is for oxygen. Yes? Okay? So the carbon monoxide is 210 times. And communities take it very seriously. When I worked on an ambulance as a medic, EMT, wasn't quite a medic, but...
You worked in the ambulance?
And ambulance, yes. And we would be called, any new construction in most places in the United States, any new construction, have hardwired carbon monoxide detectors. And oftentimes they go right to the police station or the firehouse. And if they go off, the firehouse knows it and they dispatch a vehicle. And in my community, it was automatically, you had three services were dispatched for just a carbon monoxide detector going off. You had an ambulance, that was me, you had fire, and you had police. So they really take it seriously. And people get there it could happen where people get there within 5 minutes. And it's an enormous community.
So sir, you were acting to be a guy?
Excuse me?
Did you drag the ambulance?
Sometimes, yes. I prefer to work with patients in the back, but yes, sometimes I drove the ambulance. Now, some horror stories.
Have you ever driven in Dhaka?
No, I've never driven in Dhaka, nor do I have any.
That's the main test of driving in the world.
Okay, now you've never driven in New York City. I can see. So now, excuse me. So we're going to be talking about enthalpy. Thank you. Let's get back together here. So we're going to talk about a reduction in enthalpy, correct? So we know that fire, you get this fire, but where does it come from? Well, it comes from here. This is enthalpy, right? The internal energy. Enthalpy is internal energy. The reactants and products. These are the reactants. These are the products. As I go from reactant to product, the reactants become more stable. See that? They become more stable. They're more stable because they have a reduction in internal energy. They have a reduction in enthalpy. You see that? That's where the energy comes from. So when we're talking about chemical properties is related to chemical change. What are chemical properties? In other words, what is a chemical property of oxygen? No, don't do that.
No, it's not.
No, it doesn't matter because you'll shake it. What are the chemical properties of oxygen? I don't know. How do you know? What are physical properties of silver? It's shiny. I can see that, right? I can see that it's shiny.
Sure.
What's the chemical property of water? Boils at 100 degrees. I can see that. It freezes at 0 degrees. I can see that. What's a chemical property of oxygen? I have no idea. Can you see what it is? No. I can tell you that it's colorless. Yes? Not particularly odorless, but it's colorless. It's a gas at room temperature. Those are physical properties, but what are the chemical properties? I don't know. How do you know what chemical properties are? That's key. Yes, do you know?
No, I don't know. I have a question.
What do you want to say?
Can oxygen be turned into liquids?
Oxygen can become a liquid at very low temperature. Very low temperature. It can be.
To fire?
So you're saying oxygen is very reactive. Is that what you're saying? Reactive with what?
Fire.
I don't know, but it can be reactive, right? It's reactive. Okay. But how do you know it's reactive? How do you know? I mean, how do you know oxygen's reactive?
It's a chemical formula.
But how do you know? Can you see it? Experimenting. So oxygen is reactive because I experimented with oxygen. Is that what you're saying?
Yes.
Yes? Okay. What kind of experiment did you do? Make something up.
Fire building.
Make something up.
I
How do you know what the chemical properties are of oxygen?
use a lighter to what? To higher fire? What?
To make fire.
To make fire. I use a lighter to make fire.
Use a lighter to make fire. Okay. So
Oh, I can-
what? But give me something more specific as to what you did.
So you cover a candle and the candle goes up because the oxygen is used up.
So, but wait a second, hold it. But you're saying now you're talking about candles. You went from a lighter to a candle. I'm confused. I'm confused.
Just a candle.
Just a candle.
It's lit up.
Just a candle that's lit up. So what's that? What? How do you know?
Then you cover it with.
All right, I will forgive you and I will help you out.
Okay.
You know that there's only two things available in the air. There's only oxygen and there's a candle. All right, fine. There's nothing else there. Okay, fine. So we're going to do an experiment, kind of wave our hands, but that's right. We already established that it's a perfect experiment. There's only oxygen and a candle available. How do I know what the chemical properties are of the oxygen? How do I know what the chemical properties are of the candle? How do I know?
So if you just take out oxygen from the environment, there won't be a fire.
Okay, but how do you know what any chemical property is? Or when do I know what chemical properties are? Maisha, what did you want to say?
So I wanted to say that.
You were like reading the book and you wanted to simply sound like a textbook for a second? Go ahead.
That you can't build fire with the oxygen.
What is it?
You can't build fire without oxygen.
You can't. No, you can't build a fire without oxygen. And I'll agree with you.
How do you-
What are some chemical properties of oxygen? Oxygen is very reactive with wood, with hydrocarbons, with gasoline. It burns aggressively. If I take a glowing splint and I put it into pure oxygen, it's going to burst into flame. Yes, correct. Yes, those are chemical properties of oxygen. However, chemical properties are only those properties that are obvious when the substance is in the presence of another substance. So, the chemical properties, CP, the chemical properties of a substance, S, the chemical properties of a substance are those properties, P, those properties that are obvious, that are obvious when the substance is in the presence of another substance. We'll just say S, right? We'll be consistent. Right? So, the chemical properties of a substance are those properties that are obvious when the substance is in the presence of another substance. Do you get that? So in order to establish what a chemical property is, what do you need to have happen? What do you need to have happen? You need what? You need what? You need what? You need a chemical reaction. You need a chemical reaction. In order to determine what the chemical properties are, you need reactants, go to products. You need that. You cannot find what the chemical properties are of a substance unless that substance is in the presence of another substance. Sometimes those properties are very subtle. Not every chemical reaction is an explosion. Some chemical reactions are very subtle. Some are endothermic. Some are exothermic. Did you ever hear of, do you know what exo and endothermic, you know what those words mean? Okay?
Creates more energy. More energy. You don't remember exothermic? Yeah.
Right? It's always the heat of the products minus the heat of the reactants. If this is giving off heat, correct? Yes or no? That's giving off heat, right? So what does delta H, what must it be if I'm going to subtract it? It's got to be negative, right? A small number minus a small positive number minus a large positive number is going to be negative. This is exothermic. Given off, exo, outside, thermic, heat. This that's endothermic. It takes in heat. Can you think of an endothermic reaction right now?
NaCl.
It's even chemical? Can you think of one?
Sodium and chlorine.
Sodium and chlorine together is highly exothermic. No, I'll give you one. I'll give you one that many of you know. Has anybody ever played a sport in here where you've used an ice pack, a chemical ice pack? Where you hit it, mix it with water, gets real cold, you put it on your wound. It's a chemical ice pack. Has anybody ever seen that? It's literally a bag at room temperature. You put it in your hand. It feels like whatever the temperature is outside, right? And what it has in it, it has a chemical and a little bag of water. So what you do is you hold it in your hand like this, and you hit it, and the bag breaks. The water breaks. The big bag doesn't break. You have a bag. Inside that bag, you have a chemical, and inside the bag, you also have a little bag of water. You hit it, bag of water breaks inside, mixes with the chemical, gets really cold. You know what I'm talking about? No. You've never seen it? Okay. It's actually, to a large degree, you have to register in order to even purchase this chemical. This is a very deadly chemical. It's very explosive. Ammonium nitrate. You ever hear of ammonium nitrate fertilizer? The Oklahoma City bombing in 1993, where the federal building in Oklahoma City was literally, it was an enormous building. Much bigger than this building. It's like a city block in Dhaka, right? And it was literally leveled by a bomb in a van outside. And in that van was an enormous amount of ammonium nitrate in giant barrels with fuel oil inside. And then they had something to trigger the explosion, a detonator. But what happens is, you get this and it dissolves like this. Just the dissolving process. So when I take the powdered ammonium nitrate, I mix it with water, I dissolve it in the water, and I create an cations, positive ions, yeah. Ammonia looks like this. This is the crap before. Yes? It has the structure of this. Yes? And it mixes with water and produces dissolved material. Yes? Dissolved material. This and it's really cold. I'm talking very cold. If I had a bag, I used to, when I taught at school, public school, I would ask, I'd say to a student, go down to the trainer's room and ask them if I could have a chemical ice pack. And they'd give me a chemical ice pack. And I would bust, I'd bust it, and I'd make a hole, put a thermometer in it, and it would get 0 degrees Celsius. Maybe a little below, because this is depressing the melting point.
Sure.
It's called freezing point depression. So in other words, in the winter time, when you live in northern climates where they have a lot of ice, they spread salt on the roads, and the salt depresses the freezing point, so the roads don't freeze at like -1, -2 degrees. Yes, they stay wet. So that's endothermic, right? That's endothermic, right? So you have the reactants. Sorry, you have the heat of the product minus the heat of the reactants equals endothermic, positive, right? We still got time, guys. I'm not done. Okay, now,
So is rusting,
yes,
rusting is it an endothermic reaction?
I'm going to get into that in a minute. I may not actually get to that, but I'll mention it. I'll answer your question, certainly. Okay? Now, don't forget, your homework, I'm going to make your homework due on Monday. I'm going to allow you to ask me questions on the homework on Sunday. If I don't get any questions, then that's the last time I'll put it off a day. Understood? So ask me questions. And then on Thursday, the 16th of November, is the test on chapter 1. Understood? Okay, now, let's continue. So, we know chemical change and chemical properties. Chemical properties are those properties that are only obvious when a chemical change occurs. The chemical properties of oxygen are only those properties that are obvious when oxygen is in the presence of another property. Clear? So a chemical change has to take place. Physical properties are simply obvious. They are characteristic of a substance. Yes?
Yes.
Okay, now this is key. How do you know a physical change took place? How do I know? Sometimes they're very subtle. You don't get a lot of heat. What are obvious reasons you get a physical change, a chemical change? You get chemical change by color change,
Yes, sir.
right?
Yes. Before I
You get bubbling. We'll talk about these individually another time, but you also get what else? You get heat given off or absorbed, right? But sometimes, and this is the big one, I think this is the big one. Because more times than not, chemical change is very subtle. Very subtle. Rust is very subtle. It is. Tarnish is very subtle. Things rust and corrode sometimes very slowly. Yes? When, you ready? When the property, when the properties, P, when the physical properties, and I'm talking about characteristic physical properties or intensive physical properties, when the characteristic or intensive physical properties of a substance change. You get it? When the physical properties, when the characteristic, intensive physical properties of a substance change, a chemical reaction has occurred. Because intensive physical properties are those properties that identify matter. Look, I have water, right? Okay. Water, clear, colorless, odorless.
Yeah.
right? Boils at 100 degrees Celsius. Right? Boils at 100 degrees Celsius. Freezes at 0 degrees Celsius. Has a specific heat capacity of 4.18 joules per degree Celsius. Now, I go like this. I don't care. I'm finishing. If you guys allowed me to finish before, I would have been done by now. How do I know that happened? How do I know that happened? Well, this is a gas. This is a gas. That's not a gas. Now that's not subtle.
That's a liquid.
Hydrogen is a gas. Oxygen is a gas. Water is a liquid. If I take water and I put some salt in it so it can conduct electricity, I run electric charge through the water, I'm going to convert it to hydrogen and oxygen. Now, so that's an obvious one. When my physical properties, water is a liquid at room temperature. Now I have a gas at room temperature. Physical properties have changed, haven't they? So wood, nice, blonde, maple tree, is now black, disgusting, chemical change. Its physical properties have changed. So, color change, bubbling, heating, and when the physical properties of a substance change, a chemical reaction has occurred. Understood? Chemical, physical properties, chemical, physical change. We'll talk about combustion, corrosion, which are actually chemical changes. We'll talk about that on
Sunday.
Monday.
Sunday. Goodbye.
Monday.